In the last video we managed to get the motor working so it would lift the knee. However, when we turned the power off, this happened. Yeah, let's sort that out. Welcome back to the workshop and welcome to this video series to do two things. One is to get more space underneath the chuck and the other one is to motorise the knee. So in the last video we managed to sort out the friction issue in the drive system and we can now lift up the knee. Okay, we're not lifting it at super speed, but we'll get to that. The critical thing we found though was when we turn the power off, this is so heavy, it's heavy enough to backdrive. So what exactly is going on? Well, when the ball screw turns, because of this inclined plane on here, we can apply lots of distance but a very small amount of force, and we can turn that into the opposite, which is a high amount of force but over a very small distance, in which case we can use a relatively small motor to lift a very heavy load, or on the CNC machine to lift or move a very heavy axis. And that's all great, but if you draw out the free body diagram of that and you look at where the forces go and the angles, you'll realise that with enough load on here you can actually backdrive the screw, and it's made worse as the pitch gets larger. So if you go from 5 to 10, or if you're larger and that angle is higher, you can kind of imagine that a force down is more likely to sort of push that out of the way than if it's shallow and it has quite a lot of force required to push it out of the way. But ultimately on every system there will be a force that can backdrive it, and in this case this knee is so heavy it's just enough to overcome that and any friction in the system, especially when the motor's off, when there's no resistance here, and it backdrives it and it slowly sinks down. Now this is not a new phenomenon, I'm not the first to discover this by any means, and when I was doing the manual lift system, so when I had the crank handle on there, I did do some calculations to see if when it let go, so when I wasn't applying any force, would it backdrive, and the answer was it was going to be a bit touch and go. It might do, it might not, you know, within the accuracy of the calculations, and the answer was it did very slightly backdrive when it was driving through that bevel gear and any of the friction in the system. So I was well aware that it was possibly going to be a problem, but I thought, well, we'll get to it when we get to it. Maybe the stepper will have enough friction in it anyway, even when it's off, and let's see where we get to, especially with that gear ratio. But we now know that, no, it's going to backdrive, so we need to do something about it. So first of all, I want to take this opportunity to thank everyone who commented, especially on the last video. It was really helpful. Some of those things I already knew, but some of them are new, you know, and it gives you a lot to think about. And that's the great thing about YouTube. You get this toing and froing of ideas. So let's kind of summarize the options that might be available. So the first option, and the obvious one, is to fit a worm gear on there. So you fit a worm gear on the side and drive this gear. That's great. It doesn't backdrive unless you go for some very extreme, rather silly angles on that, but in generally they don't backdrive. The downside to that is you need to turn the worm gear a lot to get a little bit of movement. In other words, the table will be very slow, so you then have to introduce a gearbox to speed it up again. So I did look into that, and in fact the DC motor that I originally had on here, you know, the little one that really was never going to perform, did have worm gear in it and a little gearbox. That was why it was perfect, and I hoped to get that to work, but clearly that was a non-starter. So worm gear, yeah, I think it's too complicated with the gearing and the extra gearbox you would need to get some reasonable speed, so I'm probably not going to do that. Another option was some kind of braking system in here. Now, those of you who remember the go-kart build might remember that I put a mountain bike brake on the electric go-kart for my daughter, and that was absolutely brilliant. You know, it was a mechanically operated via a Bowden cable, and it would squeeze these calipers, essentially, all these brake pads, onto a disc, and you could lock the back axle up while you're driving along, so plenty of braking force. So I could maybe get something in there, but there's a spring in there that you've then got to overcome to actually apply the brakes. And what you want is you want it to be naturally on when it's not powered. So you got to kind of reverse that. Maybe you'd have to take the springs out with the calipers and add an external spring that always push them on, and then the servo or the motor or whatever, or solenoid, has to be powerful enough to overcome that spring to release the brake when you want to move the system, and then depower it so that the brake goes back on the rest of the time, or if you power off the system. So yeah, maybe it was getting a little bit complicated to sort of design my own system. So what else is there? Well, I knew that servos came with brakes because on the high powered machines, particularly if you've got a big mill and you're trying to move the Z-axis or the head up and down with you typically might need a servo to get the extra power, and because they're big and heavy, when you turn it off they might sink, so you naturally want a brake. To be honest, I'd never heard of steppers with brakes, but yeah, it makes sense. A little bit of looking around, and for a 3 Newton meter motor it was about £60 to get one with a brake on it. Now I did look into the spec of those brakes, and well, two things: the motors I found were only 2 Newton meters. It's only a little bit more torque than this, so I was a little bit, I mean there might be some 3, maybe I'll need to look a bit harder, but I only found those. But more importantly, the brake, because it's only a little disc that bolts on the back with some springs and a little solenoid in there to activate the whole thing. I think you were looking at 1.2 Newton meters of torque, braking torque, and it's kind of inherent in the design because the solenoid has got to overcome the springs that are applying the braking pressure, and the whole thing's quite small. So I did do some calculations which did suggest that the backdrive torque was quite a lot lower than that, and that would be okay, but it just, combined with the fact that the stepper wasn't that powerful to start with, which had the integrated brake in the back, I was questioning whether that was the right way to go. So because things take a long time to order, a couple of weeks ago I ordered a big 3 Newton meter motor that would replace this, just to give me plenty of lifting power, a lot more speed. It's probably going to back drive, but same issue there. And I'd already ordered that before someone had said, oh, actually you can get them with a brake on. So I've then gone ahead and found the brake unit, an independent one, which I've managed to buy reasonably cheaply. I think I got it off AliExpress. So I've got options to sort of combine the two together. Now, to use that standalone on a stepper, two things. One, it needs the shaft out of the back, a double-ended. Now this is only single-ended. All the servos or steppers I've got are single-ended. And the one I ordered a while ago and just arrived, is also single-ended, not double-ended. So there's that little issue. And the second one is you need a hole pattern on the back here to be able to bolt the brake system on retrospectively. And I don't think this one has, and the one I've ordered, it has one, but I don't think the bolt pattern is going to match up with the brake unit. So the brake system's yet to arrive, but I thought, let's put the order in now. It wasn't too expensive, and it'll give me something to play around with, and I might be able to base something that I make on that and integrate it somewhere in the design. Another interesting suggestion which came up a couple of times was, well, if you take this stepper motor, let's call them coils A and B, if you actually short these out, obviously not while you're connected to the driver, short those out, it becomes very hard to turn these, and I'd experienced that in the past. I think I even put it in a video a few years back just showing that effect. But I hadn't kind of put two and two together and thought, oh, maybe it could be used as a brake. But the physics didn't really stack up, because if you join these together and you apply that force and it resists, you're getting something for nothing a little bit there. You're not cutting any of the magnetic fields. And then I think someone mentioned it was Lenz's law, wasn't it? Which I had heard of, but hadn't put two and two together. So thank you very much for that. And yeah, in theory, unless there's a bit of friction in here, it should slowly creep, and then you cut some fields and it resists, but it will slowly go down anyway, even if you short these out. Alright, so I've got the coils shorted across A and B, and I've got a clamp on the guide roller there, which is trying to stop that back driving. We've got, I won't put my finger in, maybe about 10mm of travel. So we'll take the clamp off, see if it holds, or it might still back drive, I don't know, we'll see. And then we'll undo one connection, then the other. So here we go. Ooh. Yeah, it's creeping down. Oh, it's stopped. So if I try and encourage it, it's definitely sort of better in that it doesn't just want to keep dropping, it's doing something. Wonder if you left it overnight, it would generally go down. Right, let's disconnect the coils and see what happens. Okay, it might have caught on a sticky part of the ball screw, I don't know, or this might be a genuine effect. So I'll try and keep my hand out of the way. So I'll take one out. There's one gone. Second one. Okay, I'll do the same thing, I'll sort of coax it down. It's a lot easier to turn. And yeah, it does want to go. Yeah, it's back driving there. So I think the answer is it helps a little bit, but I'm certainly not going to rely on that system. In fact, what we'll do, we'll just reconnect those, and I'll just apply a load onto the knee as if I'm drilling, and see what happens. Alright, so wires are connected again. We'll put a load on the knee and see how easy it is to overcome it. We've got a gap, so it's not back driving, and it's in a region where it wouldn't take much. If the cores are not connected, it wouldn't take much. But yeah, that's definitely having a small effect. Right, let's apply a load onto the knee and see what happens. Okay, here we go. I'll do it this way round so I don't block the view. Okay, we're touching now. Apply a bit of load. Oh, and it's going. Hopefully you can see that on camera. Yeah, that's not much load. I'm at full stretch and I'm barely pushing it. So yeah, that's that. And what we'll do, I'll just disconnect the wires. One's out, two's out. So there's no connection at all down here. Let's just try that again. We've got about 5mm to go. Oh wow, that's a lot easier. Yeah. Okay. So in conclusion, if you short out the coils, it does offer some resistance. Practically, it can still be overcome, and it didn't take a huge amount of extra effort. So I don't think I'm going to be hooking up relays and making that work. You know, if you wanted just to stop it creeping down, then yep, that is an option, and it does all help, of course. But I need a brake anyway because I need to resist the drilling load, so that brake may as well do two functions. Brake the system when there's no power, and brake the system when you are applying load for drilling. So yeah, nice idea, but hopefully we've done enough to prove out that it's probably not robust enough as an idea. But thank you very much for the suggestion, and it was fun to try it. So the other popular option was some kind of counterweight system, and yeah, I've seen that used quite a lot on milling machines and things like that as well. So you probably need some kind of strong heavy duty cable that would go up and around some kind of pulleys at the top and go out to something at the back, and then you'd be this heavy cast iron block, whatever, something like that. I wouldn't really want that rattling around, so I've seen that set inside a tube that's just a little bit larger, just so it can't rattle around and it just kind of follows that tube. But essentially this weighs probably 50 kilo. One of the things I want to do is get a bit more precise weight. So that's a lot of material to fit in a very tiny gap back there and get all the mechanism in and avoid the quill. It didn't look like it was going to work retrospectively and be a neat solution and maybe offer enough. So yeah, it was good, but there's another suggestion. So the other thought I had was, well, what about a gas strut or a gas spring? So I went ahead and ordered one, and then a few days later, a few of you guys commented on that as well as an idea. So that is one I'm going to experiment with, and to that end, it has arrived. One shot, here it is. And I ordered it. I thought it was going to come with like spherical ball ends on it, like rose joints. So this would move in a kind of olive shaped collar at each end, but it's just a simple aluminium block. So that's, you know, the photocopy of the drawing that they supply with this, it wasn't very clear, and you could have this as an end or a kind of bracket system. So I thought this was going to be a ball joint end, but it's not. But that's okay, it's just an M6 fitting, so I can order a few pound, just an actual proper rod end which has got spherical bearing on it, and then we can bolt this in, and any misalignment and any movement it can account for. So let's talk a little bit about gas struts and what they might offer. Now, I haven't got an accurate weight of the knee, the XY table, DROs, the vise and everything all up, but I'm reckoning it's about 50 kilos. So with that in mind, I ordered you can see that on there, but a 500 Newton gas spring or gas strut. We can say, what's that, YTT automotive. This is just a generic aftermarket part, automotive use. I mean, it's mainly for lifting tailgates or any kind of door, and it would generally sort of swing through an arc as it extends and compresses. But in our situation, I probably want to do it that way, so the oil sits on that seal. So I probably want to put it that way. In principle, it could go either, but I think for a longer life, probably better that way. Yeah, I'm basically just going to be going up and down because there is enough space to fit it behind here and come out, you know, underneath there. So let me just show you roughly where that might end up. So I can post it down this back here. It says. Oh yeah, and then up. So in CAD there is space, and in reality there's also space for after that to sit. So I think the way this is going to work is the lower portion down there will be bolted to the machine at the bottom, and then this top part here, this is the bit, let's just rest that there for a minute. The top part there needs to be connected back to the table. So I've drawn up a very thick, I think 10mm sort of bar that would go from the knee up to that point there. So when the knee goes up and down, it's loading the top there. So that was the general idea, and I think it would fit in and I could make that work. So that was my thoughts on it. Okay, let's talk a little bit about gas springs then. So what I've marked out here is the force in newtons and then the extension in whatever, millimeters in this case. And if we plot it out, now remember I've estimated the table about 50 kilos, which is why I've gone for a 500 Newton gas spring. It might be I need to tweak that either way. I want it to kind of be neutral somewhere in the middle, or maybe the upper third. So the motor only has to overcome a little bit to go up or to go down. It's like a DC offset effectively. And if you draw that out as a graph, maybe I'll insert a graph here just to show you what I mean. It gives you a huge mechanical advantage. Now it doesn't mean we can still drill and apply a load on that, but it solves backdrive and a load of other things when the power's off and all that kind of stuff. Also, the stepper will probably be able to lift a lot faster. So lots of good reasons to add this gas spring. So if we look at the extension here, this is when it's fully up and it's fully extended at this end, and then we slowly start to apply some force to it. Initially, I mean, we probably don't need to take this into account massively, but there'll be a little bit of stiction in the seals and so on, so we'll apply some force. Nothing will happen, it won't move. And then at some point when we overcome all that, it will start to move. We obviously need to keep applying that to force to get it to compressed. So as it's coming down and squashing, we'll go up like this. And then it will get to a point where you're pretty much towards the end of travel and you're at the maximum there. Similarly, when you let off that load, so when it tries to go up again and extend and come back this way, there's a little bit of stiction in the seals. So I guess it's gone up that way. So it's the force starts to back off, and then it will start to move and come down like that. Come down, and you could label these points, I guess, 1, 2, 3, 4, whatever. I don't know this for a fact, and this might be what I have to do some experimentation about, but in terms of the force, because everyone wants to market theirs as the best, highest figure, I'm guessing the 500 newtons is that one there. The maximum reasonable compression without smashing into the end stop is probably there. I don't know whether to worry about the stiction, probably not a big deal at the end of the day. It's going to be quite small in the scheme of things. So this is a bit of a problem because if I am, say, 45 kilos or somewhere thereabouts, my neutral point, this is all fine. I don't know what this value is down here, and therefore, where am I on here? Because I want to be probably somewhere in the middle, somewhere like that, and I want to spec it so that it kind of floats in the middle. Now, I've had a look around at the best value figures I can find, and I did find a suggestion that if I put it into these terms, this is 500, this would end up being, I think this one down here, 400 newtons. There's some gas pressure already in there, so it never comes down to zero. That's one of the great things, that kind of straighten out a little bit. It's not completely from zero. So if that's the case, and it's around 45, 48 kilos, it'll be about right. So that's why I went for the 500 in the end. Again, we'll see through experimentation if that's ideal. I think these gas springs were about £13-14, so nothing too pricey if I want to buy another one with a better spec. So essentially that's it. So I think I need to make up some parts. We can do some experimentation and find the neutral buoyancy point, and if that's somewhere around the middle, plus or minus 20%, I think that will be really good and we'll have a nice system. Okay, so before we can mount that strut, we need to make and modify a few parts. So the easiest one is this one, which is a spacer. So I've just turned that up on the lathe. Nothing too fancy there, just turn the outer to size and drill the center, and then part it off to length. We've got the upper pin there that the gas strut connects to, so it's a little bit more to that, but generally not too complicated. I think we'll make that next. This part here, this is the bit that connects between the gas strut and the knee. The material hasn't arrived yet, so we can't do that, but it's just a flat stock with a number of holes drilled and tapped in it. And then this one here, I've already made this. This is the back plate for the knee. This is just telling me where the two clearance holes need to go in. So I'll need to drill those in situ, mark them up and drill them. And they allow you to bolt between this and then this lifting strap that connects to the gas strut. So I think the next thing we'll do, we'll make that. And then when that arrives, we'll machine that. And then we need to modify that. And then we're ready to fit it. Okay, you just saw me turn down some of this pin that's going to hold the gas strut on. So we turn that down to just over 8mm. That's a nice snug fit. There's a little shoulder on there just to make sure it doesn't move all the way along and rub on there. And then we got a little a groove there for a circlip, or in my case I've just got a little box of E-clips. I couldn't find any circlips or snap rings in 6mm in a set. Yeah, I wanted a bit of a set and assortment, so I've gone for these E-clips, which are going to be fine. So I'll go in there, and this is oversized at the moment because obviously we've got to turn this down. But to put the flats on, I thought we'll stop at this point. I'll just cut it to length, put a little chamfer on. We're going to drop it into there, but before we do that, I'll just mark up. So the flats on this need to be 4mm. So if I mark at least 4, then I'll make sure when we machine those flats, doesn't matter if we go over because we're going to turn that bit down. I'll just put it in a couple of places. That's definitely enough. Alright. Also means when I drop it in the collet, I know I should leave a little bit of space for the end mill to get in. It's going to be a bit tight. Alright, so I've finished the little pin that holds the gas strut on. This is the one at the top. So we've got our thread, our flats, so we can tighten it. And our little, well, this will be an E-clip groove in there, and then that fits nicely together, so that will go in the top. We've got a spacer for the bottom, and then I've just, the stock arrived, and I've just drilled and tapped a couple of holes. So I've got a few different places we can put the top, and there were 2 fixings I need to use at the bottom, so I've got a choice there. I was going to cut it to length, which is that point there, but decided we'll just leave all this on. It will mean we can't go all the way to the bottom, but it will give me a bit of an idea about, is it going to work? Does it need a little bit longer? Because obviously I can't, once I cut this off, I can't make it any longer, or not easily anyway. Alright, so I think what we'll do, I've decided I'm going to make life easier and safer, because I've still got to drill these 2 holes here in the back plate, and that's like the back plate of the knee. So I'm going to take the XY table off, and to give me lots of space, I'll take the chuck off, and I think I'll take the quill guide off the top as well. So we'll get on with that, and it will be stripped down, and then we can easily get in there, just see if it's going to work. Then once it's all bolted in and it looks like it's going to work, I'll put the XY table on, and the weight of that should allow it to sink, and we'll find the neutral point. Right, let's get on with that. Okay, and then the last modification was just to drill out those 2 clearance holes, so we bolt on the big adapter bracket that goes to the gas strut. Okay, and here we are, the next stage ready to go. So we've got the electronics just set up here, wired in again. We'll switch those on in a moment, and we need to move the motor up and down. As you can see, I've got it backed away, just got the table propped up on that bit of wood, and then we can move the knee up and down manually just to get everything aligned and get it lined up to the gas strut. And I've done a bit of a dry assembly and then worked out exactly how long I wanted this. In the end, I don't know if you can see that line there, but I added about another 30mm just to give me some options, and drilled another 2 holes there. So we've got 4 at the top, 2 at the bottom. So we'll only need 1 of these, but it gives us a choice of where to put the top of the gas strut, and then we'll need 2 of these at the bottom, but we've got a couple of choices there just to get it completely dialed in. I think we're about ready to go. So got a few bolts, we've got the spacer we made, the pin, and then the motor's backed away. So let's get the gas strut fitted and just see what it looks like. So we get the pin fitted first. Okay, and that's the top there. And then get the E-clip on. So hope it doesn't fly across the workshop. Okay, now because I've got the quill guide removed and the chuck, we should have plenty of space to kind of thread it in down there. So it goes that way around. Is that going to work? No, maybe from this side. Okay. I think we're in. One of the other reasons for taking the quill guide off is because that surface there will exactly match this surface, the back of the quill guide. Basically they'll rub against each other. So once this is all working, my plan was to machine 0.5mm off here. My other option was on the back of the quill guide, which is here. Is to just machine out a channel 0.5mm out of this. So there's plenty of material there. It's just if I can get it on the CNC machine. I don't really want to strip it down because it took a while to get it all nicely aligned. But if I can get it lined up on the CNC machine so I can machine a groove in that, that would probably be easier. Just a little bit better overall than sort of weakening that really. Right, anyway, let's bolt this in at the bottom. Okay, so the lower one. It's going to be fun. Got to get the spacer in. as I said earlier in the video, obviously this is riding on those threads, which is not ideal, but it's it shouldn't rotate or move, it should just go up and down, so you know it's not going to rub into the threads. Maybe it'll be okay, you know, but if not, I can either machine a new end, or machine that out very slightly and put a sleeve on it, or machine a custom shoulder bolt. But we'll worry about that another time. I'll just get that loose for now. And then we need to bring the table down a bit and get this lined up. So I'll take the wood out and support the table. As you can imagine, I wouldn't really be able to do this with the knee on it. Somewhere about there. Let's just get that squared up before we tighten it. Okay, I got to the bit where I didn't really have a plan about how I was going to do it. I thought we'll get to this point and then work it out. So basically we've got the strut connected. I've just reconnected the ball screw, so it's connected on the bottom of the table, because I tried pressing down on it without the ball screw just to try and get a little bit of preload on it, try and get it to break the stiction on the strut, but I can't move it. So the problem I got really is the XY table is really heavy, and I think to lift it, I'm basically going to be lifting it, well, not far off my shoulder height. I mean, I could probably do it, but I don't know if I can get it up and onto there. So another option is to use the ball screw to pull it down. Now at the moment I don't have the retaining collar on because, you know, I was never intending to have huge upward forces, which is, you know, when I start pulling this down on the gas strut, it might just simply pull the whole drive assembly out of the bearings. Yeah, it was never really designed for that upload. So what I might need to do is redesign the interface, so that sleeve, to make it a lot longer, and then I'd have an axial bearing like this on the bottom as well. So I've got an axial bearing top and bottom, and then a collar, or more likely a threaded nut with a lock ring on it, so it can actually take load in both directions. So I don't know, I might try just pulling it down and see if I can break the stiction at least, but there's every chance this might just pop out, but we'll see, because we need to get it a bit lower, so I stand a fighting chance of getting the XY table on. And then my plan was I could back the screw off with the bolts undone, and it will lower this down. Then at some point it should find a medium, where, you know, a neutral point, and we can just see where we are on the travel. Right, let's switch this on and carefully lower that and see if we can break the stiction at least on the strut. Can't be 100% sure, but I think what's happening is the ball screw is trying to pull this down, and because the gas strut's pushing up, basically it's just putting huge moments, bending the table down against these rails, which they're never going to resist that, especially with a single carriage on there. So I think what I might have to do is find a way to get the XY table up onto here, and then we can use the weight of that to actually push down. But just thinking where all the forces are going to go. So we've got the centre of gravity of the tables about here, we're pushing up here, but that's there, so we are going to get a moment on that. This might all go horribly wrong. I want to ponder about whether this is really going to work, and if I just made a huge mistake in just the way that's going to work at the back there. I was chatting to a friend of mine who's very experienced with gas struts, and he's given me some spreadsheets and things like that. And he did make quite an interesting suggestion, which I guess is obvious now when you look at it, which is maybe you could run the gas strut maybe one side, or half the pressure and put one each side, but basically go at a diagonal across like that. Nice thing about that is that you can kind of straighten out the curve a little bit, so you gain. So when the pressure's the lowest, then you're pushing more straight down, and when the angle's like that, you gain that mechanical advantage because you're going down. So it's like the sine of the angle or cosine of the angle, and maybe you just flatten out the force. And if I did that, that would be possible. I think what I'd be tempted to do, rather than come out to here, is work out where the C of G was, which is somewhere up here in height, and try and make the strut go through that. Just thinking about where the forces would be, it would minimise the moment a little bit. I think there'd still probably be a little bit of one, because you never get it perfect, but it'd be a lot better than it is. So that is an option. I could put two, one each side, and I'd have to work out the travel and geometry and things, but probably go from there to there. I'd guess C of G is probably about here. Options. Anyway, I think the only way to try this is really just to take my time, but get that XY table onto there. Okay, I've made it a little bit lighter, at least by taking the vise off. It's surprising how heavy that was, so that's lightened the load a bit. But reluctant to take this off because it did take a while just to dial it in and get the gibs set just nicely so it ran orthogonally to the base. So yeah, I've got a piece of wood just jammed under the front there, just so when we get the load on there, that will support it if it's going to try and move this way, and then we'll just take it from there. Right, I paused at this point in case something disastrous is going to happen. So I was just having a look at the moments and the forces involved, and the first thing I did is just have a little look at the specs for HD20. You probably can't read that, but just looking at the maximum moment you'd be allowed to put on it, which is MP, and again you probably can't read it, but I'll show you on the paper in a minute. MP, depending on exactly the style, but it was between 0.2 and 0.35 kilonewton meters. So what does that mean? Well, I've done a quick diagram here of the knee. So that's the center of gravity for the knee, the mass that's coming down. The ball screw is very close to that. It's probably within about 10-15 mil. And that's the force going up from the ball screw. And then we've got the other force, which is the gas strut here. Now I've drawn it actually in front of the linear rail, but in reality it's actually very slightly behind. And then we've got distances. A is the distance for the gas strut, B distance center of gravity, and C distance to the ball screw. So we've got all the forces, we've got distances. Right, so I think as I was just saying there, HGH is 20CA or HGH 20HA, depending on exactly the slight differences in style. Between 0.2 and 0.35 kilonewton meters of torque maximum, kind of this way, as I've drawn the arrow there, which is 200 to 350 newton meters. So if we take like lowest end of that, which is 200, what does that mean? Well, if we take our gas strut, which is very slightly behind the bearing, so 10 mil, so turn that into meters, 0.01. The knee is obviously ahead of that by 170, turn that into meters, 0.17. The ball screw, although I've written that down here, we can ignore that, I'll tell you why in a minute, but that's about 150, so 0.15 meters. So they're the distances, and then in terms of forces, so we've got the knee, the mass of the knee is about 45 kilos, so it's about 450 newtons. I've put the force of the ball screw as 0, because you can imagine a point where, worst case, is where you've got this to just the right height, where these two forces basically are the same. So the knee, the ball screw isn't applying any force. And in that case, then the gas strut is also at 450. So we've got 450 from either from that and from the strut, and that will be our neutral point. And if you look at the moments, so 450 times 0.01 plus 450 times 0.17, because the gas strut's acting behind there, and the mass of the knee is ahead, so they're both trying to apply that same. It's an additive torque on there, additive moment. I've ran these numbers a couple of times, and it comes in at 81 newton meters, which is what, worst case, and we can take up to 200. So maybe I'm worrying over nothing and this will be okay. It just doesn't feel like the best idea. You know, if I was starting from scratch, I probably wouldn't quite do it like this. But anyway, looks like that should be okay. So let's lift the knee on and see what happens. So I've just got another piece of wood at the back there, so it can drop, what, 30mm? Because I'm going to knock this one out now, and this might back drive until it finds the neutral point, or something really bad might happen, I don't know. Still not convinced about that moment, but the calculations seem okay. What we'll do now, we'll just drive the motor down and just make sure it doesn't try and lift out that bearing and see if it actually sinks against the gas strut. There we go, going down. Just see the table kind of bending like that. That gas strut is not compressing. I've got the table kind of down a bit, so it's trying to push against that, and I'm just going to see, just beginning to wonder if this gas strut spec'd correctly. Oh! That moved a bit. It might just have stiction in it, and once it's had a few cycles it'll be happier. Just go down a bit. Okay, might as well do both at once. Is that going down? I'll just lower the block to give me a little bit more of a gap. It is compressing it, but only when I put a little bit of force on the crowbar. So it might just need cycling. Oh, I've just noticed something. Yeah, it's doing what I feared it would do. So you can see it's lifting itself out of the bearing because I haven't got a stop on the other side. So yeah, I'm going to need to re-engineer that anyway. But I guess that means I should be able to push it down a bit further. Use the crowbar and close that gap up again. Oh, there we go, yeah. Oh, we found a neutral point. Or this gas spring is rated higher than they said it was. Alright. Tell you what, we'll go back up again. We should get to a point where... Yeah, and stay down. Alright, okay. So what can we conclude so far? It looks like that gas strut's actually higher rated than the spec. because the neutral point where it wants to start and pull that out of there is pretty near the top, so it doesn't take much. Either that, or the curve that I assumed it went from 500 down to 400 newtons, maybe it's flatter than that and it stays nearer the 500. That's one option. In terms of, so if it doesn't feel like it's like a spring ready to fly out. That feels okay. I think maybe this is going to work after all. Probably need to get a lower spec strut, maybe go quite a lot lower, because really I want the neutral point to be somewhere a lot lower than that. And £13 each, that's not too bad, even if I then buy a second one after that to dial it in. So I think what we'll do, we'll play around with this a little bit more and get a feel for it, and then we'll bring you back and kind of summarise where we're at so far. So you can see that's starting to lift out there even without any preload from the crowbar. So we've kind of reached the balance point now where the gas strut's able to pull it out of the bearing. So I don't know if it's showing up that well on the camera, but that's where that started at 0 there, and we're currently about here. That's our balance point, and the total travel I think was 225 millimeters. Let's just measure that. That's gone 50 mil. Let's write that on there. And we need the total 225. So it's going to go to there. Alright. Now I don't have the mass of the vise on here, we've not got whatever we're drilling on here, the mass of that, but even so I think this is a bit high. So we need a lower powered gas strut, maybe even half as much, just to experiment with that and see what that does. But we did get there, and I know this is under pressure, but that feels okay. So I think there's just a lot of stiction in the gas strut, and hopefully it will bed in. If that was really tight, putting loads of force in, then I think you kind of feel it from that. Right. I just need to have a think before I dive into where I'm going to go next. Now, I was hoping to have this working and get to a nice point in this video, but I think I need to go away and do a few calculations, just see, maybe order 2 gas struts in and get that tuned nicely. I also clearly have got to re-engineer the drive system down here so it can take the loads in 2 directions. I was kind of thinking I'd have to do that not long after I made it, to be honest. But back then I was thinking it'd all be vertical loads that way only. So I think we'll call the video there. Hopefully you're enjoying the progress so far. I think this is going to work. I think we're okay. Just need to tune it in and get it dialed correctly so we get the right kind of support, and then re-engineer that bearing system down there. I've also got the brake system on order, so that's coming in about a week and a bit's time. That's the electric brake, and then I've got to work out how I'm going to integrate that into this, because it doesn't bolt directly onto the back of the stepper, because there's no shaft coming out the back and there's no bolt hole to connect it. So got a few ideas, might have to make some custom brake system on there to get that embedded. Alright, I think that's it for now. So if you're enjoying this video series, feel free to subscribe, ring that bell so you get notification when you want to see the next installment of this exciting adventure, see where we go next. With that being said, thank you very much for watching, and see you next time.